everyone. Welcome to Let's Talk Astrophysics. I'm so glad to have you join us today and learn everything about what's cool, what's going on in astrophysics right now. I'm your host, Natalie Wallaby, and I'll talk a little bit about myself, but let me share my screen real fast and we'll be going through a few logistical items first. All right, so I'm sharing my screen, I'm sharing my slideshow. Hopefully everyone can see that now. Okay. So I am actually going to leave it like this, just so I can have some other notes that are up. I'm going to start off with land acknowledgement before we get started. So first, Let's Talk Science acknowledges the diversity of Indigenous peoples within the land we now call Canada, and values the historical and contemporary contributions of these peoples in each region where we live, work, and study. We are committed to working toward meaningful reconciliation and continuing to broaden our understanding in these areas. In particular, we recognize the importance of Indigenous ways of knowing to our understanding of the natural world. We also have lots of people who are organizing this event who are from Queen's University. So Queen's University is situated on traditional Anishinaabe and Haudenosaunee territory. Acknowledging the traditional territory on which we live and work is a small but important step that reminds us to learn more about the Indigenous peoples in these regions, to consider the history and ongoing colonialism on this land, and to reflect on how each of us can contribute to reconciliation. The Kingston Indigenous community continues to reflect the area's Anishinaabe and Haudenosaunee roots. And I am in Montreal right now. I am a member of the University of Montreal. So the Université de Montréal is situated on land where, long before the arrival of the French, people of many Indigenous nations came together and interacted. We wish to acknowledge these nations, their descendants, and the spirit of fraternity that presided over the signing in 1701 of the Great Peace of Montreal, a treaty that fostered peaceful relationships between France, its Indigenous allies, and the Haudenosaunee Federation. The spirit of fraternity that inspired this treaty serves as a model for our own university community. I know there are people joining us today from all over Canada. We are so fortunate to have people from all over and even internationally. You can visit www.whose.land to learn more about the land you are on and who it belongs to. So I wanted to give a few words also about the people that are organizing this fantastic event. So first, the IDEAS Initiative is a national organization dedicated towards eliminating discrimination in STEM, or science, technology, engineering, and mathematics. The initiative seeks to promote advancement of underrepresented groups in STEM across all levels of education through an innovative intergenerational approach. And Let's Talk Science, which you might have heard of before, is an award-winning national charitable organization that has been providing engaging STEM-based programming to Canadian youth for over 25 years. With volunteer outreach sites at over 50 universities, colleges, and research institutions, they are committed to developing the critical skills and interests needed for successful futures in STEM-based careers for youth across Canada. And I actually did a lot of volunteering with Let's Talk Science when I was a grad student at Queen's, so I really enjoyed my experience there. So before we get started with the main program, I wanted to tell you a little bit about myself and why I'm excited about astrophysics and why I'm excited that you're excited potentially about astrophysics. So I am Natalie Wallaby. I am an astrophysicist. I obtained my PhD at Queen's University in 2016, so it's already been a little while now. I'm currently the coordinator of the Institute for Research on Exoplanets at the University of Montreal, and I am also the outreach scientist for the James Webb Space Telescope, still based out of the University of Montreal, but also working very closely with the Canadian Space Agency. So I'm very, very fortunate to still be working in astrophysics. So I can tell you a little bit about my work. What I work on specifically is galaxy formation and evolution, specifically galaxies that live in groups. Galaxies are very social creatures, and I am interested in one group in particular called the Virgo cluster. This is the heart of the Virgo cluster here, and you can see lots of galaxies. They're hanging out together, they interact with each other, and so I really enjoy understanding how these galaxies form and evolve in these groups. I mentioned that I'm also the coordinator of the Institute for Research on Exoplanets. My own research isn't so much about exoplanets, but I am learning more and more every day about this new field of exoplanets, and I'm super excited because it's a booming field. So an exoplanet is a planet like the ones we have in our solar system, but they orbit stars other than our sun. They are beyond our solar system. And so where I work, people are looking for these exoplanets, but they're also trying to find alien life on these exoplanets, which is super, super exciting. It might not be little green men, it might be biological life in the form of microbes or germs, but still, we're trying to answer the question, are we alone in the universe? And then my other big project right now is the James Webb Space Telescope. Here's a picture of me visiting it in California a few years ago. And this is a particularly exciting year for this project because it is set to launch this fall. Finally, it's going to be the successor of the Hubble Space Telescope, which you might know about. Much bigger, about 3 times bigger, looking at infrared light instead of visible light. And it's going to do lots of stuff in the field of galaxies, in the field of exoplanets, and it's just going to revolutionize the entire field of astronomy. So very, very excited. So that's a little bit about me, but we are hoping that you are going to learn lots of stuff about different parts of astrophysics during this 2-day event. And we are really in a crucial golden age of astronomy and space exploration. So you might have seen in the last week, we had the NASA Perseverance mission successfully land on Mars. There were some really, really stunning pictures of the satellite sort of lowering down the rover on its sky crane that came out yesterday. And we have missions to bring astronauts back to the moon soon. So it's really, really fantastic. Lots of interesting stuff going on in space exploration. But there are lots of stuff to do here on Earth and from telescopes in the sky as well. So in the next 10 and 20 years, we have a new era of telescopes that are going to be giving us lots and lots of new data, be it from really, really large telescopes on the Earth, like the 30-meter telescope, the extremely large telescope, who have mirrors 30 to 40 meters large, so they can see things that are very faint. We have the Vera Rubin telescope that's being built in Chile, which will be able to take a picture of the entire southern hemisphere sky every 3 nights. After James Webb, we're still thinking up of these new telescopes that we're going to send. We have LUVOIR here that you can see on my slide, which is going to be even bigger than James Webb, and it's going to be looking at visible wavelengths just like Hubble. So lots of interesting stuff for us to do. So I want to take a moment to thank our sponsors for this event. We have, of course, Let's Talk Science and the Ideas Initiative that I mentioned before, the McDonald Institute, the Arthur B. McDonald Astroparticle Physics Research Institute, which is based out of Queen's University, but with many partners, Snow Lab, which are a fantastic laboratory in Sudbury where they do lots of interesting particle physics experiments and others, Queen's University, and also a special shout out to Binder for all of their computing resources that they're giving us during this weekend. So that's it for these slides. We're going to start off now with our first speaker, and I'm super excited for the speaker in particular. I don't want to play favorites or anything like that, but first off, we have Dr. Lee-Waddell, and we actually worked on our graduate studies together at Queen's University. So she is currently in Australia, and it's like 2 a.m. over there. So props to her for like joining us at this time. She's currently the project scientist on the WALLABY survey and the first director of the Australian SKA, or Square Kilometre Array Regional Centre, at the International Centre for Radio Astronomy Research and CSIRO. Her research allows the amount of dark matter to be calculated and has even helped in the discovery of 7 new galaxies. When she's not stargazing, you can find her playing Pokemon Go, and I'm sure there's lots of places in Australia, the Australian outback, for her to do that. So I'm going to invite her to share her screen now, and then I will leave the floor to her.
Hello, everyone. Thanks, Natalie, for that introduction. So yes, today I'm going to be talking about surveying the nearby universe using WALLABY. So a lot of details in there, but I'll go through it. But first off, I'm going to start with a little bit about myself. So as Natalie mentioned, I'm all the way down here in Australia, Perth actually. And I've marked an X up here where Queen's University is. And so I'm located around 18,000 kilometers away from all of you. And so through the magic of technology, I'm actually able to give this talk. And yes, it's like 2 a.m. here, so bear with me a little bit. And I'll tell you why I'm in Australia in a little bit. But let's start with let's compare Australia to Canada. And it's actually not that different. So Canada has forests and rivers and mountains, and so does Australia. Canada has flatter areas like the prairies, and Australia has dry areas like the outback. There's also a lot of trees here. You might notice that Canada has a lot more snow, and I believe you guys just got hit with a snowstorm, whereas down here, we're actually in the middle of summer. And we also have big cities. And so on the right here is Sydney. So I lived there for a few years. And on the left, you might recognize it as Toronto. And I was actually born in Toronto. And I actually grew up not too far from there. So I grew up in Hamilton, which is just southwest of Toronto. And growing up in a big city, I never really got to see the stars. And so this was kind of my night sky. You can kind of make out a few faint stars, but not too many. And then one evening, when I was around 9 or 10 years old, my sister actually brought me out to a more rural area. And then she showed me the stars. She opened her sunroof in her car and started to point out a bunch of constellations. And from that moment, I was hooked. I realized I want to know what is out there. What are all these giant balls of light that are out there, and what is actually going on with all of them? And so from that moment, I started reading as much as I could, and I even got a telescope and everything. And so that led me into my educational background that's listed here. And so I did my undergrad in physics with specialization in astrophysics at McMaster University in Hamilton. I also did a classics degree because I wanted to understand why the planets were named the way they are named. So classics is like Greek and Roman history. And then I went to Kingston and did a master's in space science at the military college and finished off my PhD while Natalie was there as well doing her PhD at Queen's University. And during that time, in my spare time, I was also in the military. And so I was an active reservist in the Canadian Forces. And so you can just see that it wasn't quite linear, but mostly it led me to my current career path, which is being an astrophysicist. And my job is to try to understand the universe. That's a huge job, right? The thing is, I'm not doing it alone. I actually have the help of a lot of people out there. And I'll list a few as I go through my slides. And so as an astrophysicist, I'm actually an observational astronomer. And so what that means is I go to telescopes, or I use telescopes to actually look out into the universe to try to understand what's going on. And so you can see I've traveled the world. I've been to places like India, Puerto Rico, New Mexico, and obviously down here in Australia. You notice a bunch of the telescopes that I've shown here are actually located in Australia. And that's why I'm down here, because they have a whole bunch of telescopes. And so you might notice that these telescopes are big dishes. So they're not quite the ones that you'd use possibly in your backyard, or that you might see that you actually have an eyepiece that you look through. These ones actually look in a different part of the electromagnetic spectrum. And so that's a big sciencey word, I know, but I'll explain it a bit here. So the electromagnetic spectrum is basically light. And so we have optical light, and so that's what you see. And so that's what you can see with your eyes. And so a rainbow of colors, right? And so we have reds and blues and all those colors. And optical light actually, when we look out into the universe, that shows us the stars. So similar to the sun, right? The sun is bright to our eyes. Thing is, if we look at different parts of the electromagnetic spectrum, we can see different parts of the universe and different parts of galaxies. And so it's similar to how a doctor might look at a patient, right? And so if we're looking using our eyes, you can see a person, right? But if a doctor, for example, wants to look at a patient's bones, they'd use x-rays. And so we can actually use x-rays to look out at galaxies to actually probe and see like the really hot areas that are forming, such as like black holes and all these other things and activity that's going on with that. We also can look in a more cooler regime, such as infrared. And so the James Webb Telescope that Natalie mentioned will be looking at infrared. And infrared would be similar to like when you're in movies and they might have like spy goggles where they can see in infrared and they're seeing the heat, right? And so that's kind of looking at like a temperature thing. And so we can see the warm dust in infrared. And so, If we go further into the cool part of the electromagnetic spectrum, we're into the radio regime, and that's actually what I'm looking at. So I'm using these big dishes that you saw in the previous slide to probe the radio area of the electromagnetic spectrum, and I'm specifically looking at the gas. And so similar to gas that you might breathe, oxygen, of course that's at a different wavelength, but it's a gas type of thing. And so similar to how a doctor might use all these different things to look at a patient, looking at their bones, using x-rays, possibly checking out their temperature using infrared, for example, if they have a fever or something, we're doing the same thing when we're looking at galaxies and looking outwards into the universe. And so we're probing all different parts of the electromagnetic spectrum as shown here. And so this here is actually the same galaxy in 5 different panels. You can see it looks similar, but quite different as well. And so we can see all different parts of it. And so let's step back one little bit. So what are galaxies? So galaxies are these large gravitationally bound systems that consist of stars, gas, dust, and dark matter. And they all kind of bunch up and form these different shapes. And as you can see in these pictures here, they actually come in a whole variety of shapes, sizes, colors, and compositions. And based on what they look like, actually that tells us a lot about their history and how they've actually changed over time. And so you can see in all these pictures here, all these have a different type of background, and that's why they became how they are, how we see them today. And by probing them in different parts of the electromagnetic spectrum, we can actually see all the details. And so, as I mentioned, galaxies contain stars, gas, dust, and dark matter. Thing is, when we look at this breakdown of the content of the universe, there's actually a lot of dark matter in the universe. And so dark in the context of what we're using it as is more like we don't really understand it opposed to it being black, right? And so we have dark matter and dark energy. And there'll be 2 presentations later today that will kind of further elaborate on dark matter and dark energy. But you can see here that dark matter and dark energy actually comprise 95% of the universe. So that's the stuff that we don't really know much about, whereas 5% of the universe is what we do know. And so about 4% is hydrogen gas, and that's what I'm mostly probing using those big telescopes. And then the rest of it is in stars and neutrinos, and then heavy metals. Heavy metals are anything that comes from stars, so any elements that are larger than hydrogen. And so pretty much we're all made from stardust, right? And so that's the other part of this. And so this dark matter content, this dark matter actually forms in kind of halos. So they surround these galaxies that contain these stars and gas and dust. And so we have these large halos of dark matter. And that's actually how the universe is changing over time. It's actually controlled by these dark matter halos. And we know that we have these halos around our galaxy because we can measure them. And so here is a galaxy that's shown here, and it's a spiral galaxy. So that's similar to our Milky Way galaxy. So it's spiral and has these arms. It has a lot of gas and dust and stars, obviously, in the middle. And so if we measure it, we can get these rotation curves. And you're going to be doing this, actually. You're going to be getting rotation curves throughout this workshop. You're going to be working with actual data. And so you can see here, as we measure a rotation curve, as we're plotting, so this is distance from the center of the galaxy, which is pointed here, and then its velocity. So this is how fast it's rotating. And so as we go outwards, when we measure it, we can actually see that this rotation curve flattens. And this flattening of the curve is actually how we infer that dark matter is there. And so as you can see this dashed line here on the bottom, if we just assume normal physics, we would get this curve that kind of dips down because as we can see the content, the starlight kind of fades out, the gas kind of decreases. And so as we get further away, you would expect that the rotation curve would flatten. And so that's using the physics that is pretty much, when you think about it, let's use an analogy. And so let's take a figure skater doing a spin, okay, if she's rotating. And let's say the figure skater's arms are out, right? And so her mass is kind of distributed onto like a larger area. And so she actually spins a bit slower. Whereas if she brings her arms in, she can spin really fast, right? And so that's concentrating the mass. The thing is, if we put those arms out, we'd expect her to spin slower, right? The thing is, she's not spinning slower. She's actually spinning much faster as we go out there. And so she actually has weights on her arms. So it's like heavier out there. And so that's how we infer the dark matter content of our universe. And so you can see hydrogen gas, which are these blue dots here, is going even further out when we're measuring this flattening of the rotation curve. And so I'm actually using these large dishes to measure this hydrogen. I can see that galaxies are contained in these large halos of dark matter, which is mostly just gravity. And so it's pulling everything together. And that's what we understand with dark matter. It's this massive type thing, force, let's say, that's pulling everything together. And so here is a simulation. On the left side shows dark matter, and on the right side shows gas. And so this is from Illustris. And so you can see, so it's time since the Big Bang. And so as time moves forwards. So you can see this web of actual dark matter, and that's how we see the universe. So the universe is this cosmic web. Everything formed within these dark matter filaments, and they're all connected somehow. And as time goes on, you can see these filaments start to get a bit brighter. And it's actually because everything's grouping together. And so this gravity force that dark matter is made of is actually coming together. And we're getting these large clumps. And so on the right side, that's kind of similar to how the gas is coming together. So we know that as dark matter is coming together, it's also pulling its gas and content and all that stuff. So all the galaxies that contain the gas into these what we call groups or clusters of galaxies. And so you can see that as we move forward, we're getting brighter and brighter areas. And so these clumps are getting bigger and bigger and bigger. And that's done because dark matter grows in a way that we call it hierarchical growth. So pretty much hierarchical growth is when small things come together to make medium things, and medium things then come together to make larger things. And so you're just stepping it up, right? And so that's how these dark matter halos are actually growing. And as these dark matter halos are growing, so are the galaxies that are contained within these halos. You can see the gas there on the right is actually starting to form and do a lot of interesting things in the simulation. And just to summarize that a bit again, using that new term, hierarchical growth of dark matter halos. So again, galaxies are within these large dark matter halos that we're probing using telescopes and measuring data, and we're seeing these flat rotation curves. So we see that extra mass out there. And so how we understand it is that small halos contain small galaxies, right? And then these small halos merge together to form bigger halos. And then these bigger halos, within them, the galaxies also merge together. But pretty much it's just small things coming together to make medium things, coming together to make larger things. And that's hierarchical growth. And so we can see that with how galaxies are changing over time. And so what I normally study is this interaction, this growth, this merging of these halos. The thing is, as these halos merge, the contained contents also merge. And so the galaxies within merge. And so when we have, and so here you can see dwarf galaxies, and so those that's our term for small galaxies, will merge together and they'll make medium-sized galaxies. So medium-sized galaxies would be similar to our Milky Way type galaxy, right? And so it's like these spiral arms, and those are kind of medium-sized galaxies. And then medium-sized galaxies can merge together and form large elliptical galaxies, this final stage here where there are large elliptical ones. And so mostly I study this interaction part where these medium galaxies are merging together to try to understand how this interaction is happening. And then we can also understand how the dark matter is merging together. So we're trying to understand that physics is coming out of this. And so, like I said, I'm using hydrogen to probe what's going on with these interactions, right? And it's because we want to use all different ways of looking at something. Again, right, like a doctor using x-rays to look at your bones. Well, let's look at using radio. So this is actually an optical image of 3 galaxies. So they're labeled here. So we see them here, and they're very bright. They're mostly similar to our Milky Way. They're kind of disc-like, and they have these spiral arms. And they're kind of the same color, but we don't really see too much more about them. So we can measure pretty much their stellar mass, so how many stars they have in them. We can measure things, possibly their age based on their color, but that's kind of where we're going with optical. When we add in hydrogen gas, from those big dish-like galaxies, we can see all this gas. And so this gas is swirling around in the outskirts of these galaxies. And you can actually see they're merging together. They're actually doing this almost dance as they're coming together to form these larger galaxies. So the halos that are coming together are forming larger halos. And so the galaxies within them actually dance together as they merge together. And so that's mostly the physics that I'm trying to study. And so to do that, right now I'm using the Australian Square Kilometre Array Pathfinder, or ASCAP. And so ASCAP is located in Western Australia, and that's the main reason why I'm here. So it's a fairly new telescope that's built in the middle of the Australian outback. You can see it's very red and very dry out there. And the reason why it's in the outback is because, remember when I mentioned that thing about living in the city and I wasn't able to see stars with, using my eyes? Well, the thing is, using radio waves, if we have things like cell phones or radio towers, that also blocks and impedes our ability to see the signals coming from the universe. And so we're out in these radio quiet zones, radio quiet areas. And so we can use these telescopes to probe the universe. And so you can see there's all these dishes. There's so much technology that went into this. So I work with engineers that built these telescopes. We have these large supercomputers. And so there's a lot of programmers, software designers, and everything that put this together. And see, the data comes right to Perth, where I am right now, and comes into our supercomputing center. And from here is where we process it and actually do our data analysis. And so I'm working with engineers, data scientists, computer programmers, and everyone, and of course, scientists and other researchers to do all this work. And like I said before, my job is to understand the universe. And that's not a simple job, but that's why we're all working together. And so this is actually an international telescope. So a lot of people use it to do their science. And so the main survey that I'm part of that uses ASCAP is the WALLABY survey. I mentioned that during my title. So the WALLABY survey, and a wallaby is this little furry animal right here. So it's like a small kangaroo. And because we're in Australia, we named our survey after, an Australian animal. And so WALLABY stands for Wide Field ASCAP L-Band Legacy All Sky Blind Survey. Yes, that's a mouthful, eh? That's why we call it WALLABY. And so wide field, so we're trying to survey the entire sky. So as much as we can, we're using ASCAP, that's the A. L-band means that we're looking at that hydrogen gas, that gas that shows that interaction that I showed you. Legacy means this survey is going to be so big that there will be so much data that people will be able to analyze it for years to come. And so some of you eventually might be working on this data. All sky, again, is kind of repetitive of the wallaby, and then blind is defining it's not targeted. And so we could look at specific galaxies, or we can just survey the entire sky and not actually try to focus on one region or another. And so wallaby will actually survey 75% of the entire sky. So as high north as we can see and all the way through the southern hemisphere. And we should detect hundreds of thousands of galaxies. And we're looking at all these galaxies because we're trying to do a survey. We're trying to understand how the universe is working. And to do that, we have to understand all parts of it. And so similar to if you're surveying humans on Earth, if you just looked at one person, if you just looked at me, you think that everyone on Earth is female. And we know that's not true, right? And so you have to look at every person on Earth to understand people, right? And so similar to how we're looking at galaxies, we want to see as many as we can and try to understand how they relate to each other and how they're distinct from one another. And so that's what wallaby will do. And so here are a couple of maps from the wallaby survey. And so these are less pretty because these are more scientific. So they might be similar to the ones that you're working on. And so on the left here, there are actually the galaxies that the wallaby survey was looking at. So there's two of them here, and the blue lines show the hydrogen. So that's the gas that's in the galaxy. And the darker background image is the stars. And so you can see here that the stars are kind of focused in the center where they usually are the brightest, and the gas is more on the outskirts. And then if we go to the right side, you can see these rotation curves, those things I mentioned before, and something that you might be familiar with by the end of this workshop. So here are these rotation curves. And so we can break it down into different components. And so we have the gas, which we have moving faster again. So this is velocity and this is radius. So that's coming from the center of the galaxy. And so as we move further out from the center of the galaxy, we have more mass from these things. So for here, it's the gas, this blue line here. Then we have the stars, which kind of fade out as we go a bit further out. And then as we add everything together, we can actually probe that the rotation curve is flattening here. And then so this rest of the content is dark matter. And so you can see as we go out much further from the center of the galaxy, the dark matter content is quite large. And that's why we have these flat rotation curves. And so here is another example of data from WALLABY. And so the first panel is an optical image. So that's where we see the stars. And again, you can see 3 galaxies. They're actually quite blue, which actually means they're younger generally. And so that's just something that we can see from the stars, right? But then we want to add in extra information like stuff about the gas that's going on. And so WALLABY provide us the gas map here. And so this is so you can see the hydrogen gas, and we can see all these galaxies are connected, and they're actually forming something that's bringing them all together. And if we were to superimpose contours of this hydrogen gas onto the galaxies, you can see that it's connecting all the galaxies. And so the galaxies are interacting, growing, and becoming bigger because of the dark matter halo that are growing hierarchically. And so, just my last slide here, WALLABY will be making a lot of these maps. And so here's just a small map of a cluster. It's called the Hydra cluster, not too different from the cluster that Natalie mentioned, the Virgo cluster earlier. And so we can see hundreds of galaxies just in this small little portion here. And so we're already analyzing this data, but we're going to survey 75% in the entire sky. So we're going to go up to just about 3/4 of the sky here and survey everything downwards. And so that will be hundreds of thousands of galaxies. And like I said, we want to probe everything. We want to understand how the universe is changing over time, especially in these galaxies. And because this is a legacy survey, there's going to be a lot of data. Not one scientist or not one team can actually analyze all this data. And like I said, with the legacy survey, there'll be data for years to come. And so many galaxies that you guys will be able to possibly analyze if you continue in this field. And thank you.
Great. Thank you so much, Karen. Clap, 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 clap. I'm sure everyone is clapping at home, even though we can't hear it. We're going to take a few questions now. So if you have questions, we invite you to use a Q&A feature on this webinar. We have some great volunteers who are answering some, very knowledgeable, but we will also have our speakers answering some of the questions. So I'm going to start you off with a doozy, Karen. What is the difference between dark energy and dark matter?
Well, dark matter is that gravitational pull that we feel, right? And so that's gravity, whereas dark energy is more like something that's making the universe expand, and that's pushing outwards. And so that's about as technical as I'd get about it, because there will be 2 talks today that will further go into those things. So they're not quite the same, but the dark part is, again, because we don't fully understand them. Most of the dark matter that we're looking at is we're inferring that's there. That's the whole, we can see the results of it, but we can't actually see it directly. And so that's why it's kind of dark as well.
Yeah, dark, because we don't really know what's going on. There's a lot of work to do. We only know about 5% of the universe, so lots for all of the people attending to work on later on. So why are there so many big telescopes in Australia? Was data collection affected by the big fires in Australia last week?
So that's a 2-part question. So there's a lot of telescopes here because there's a lot of areas where it's radio quiet, mostly. So again, we want to build telescopes in a place where terrestrial, so what we do as humans doesn't interfere with the signal, right? And so there's a lot of outback where there's not much human life at all. There's usually more kangaroos than humans out there. And so we can build these radio telescopes that's probing the universe. And so again, you don't want cell phones out there, right? And so find somewhere that doesn't have a cell phone signal, right? And that's where you want to build your radio telescope. And so we have a lot of those areas in Australia. And there's a bunch of them here just because we do want to probe the whole universe. And so we want to look at the southern sky as well as the northern sky. So there's a lot of telescopes in the north as well. I just pointed out a few that were in the south that I work with. And as for the fires, for the most part, they're quite under control. We do have issues sometimes with evacuations and whatnot, but they're pretty good with handling fires. And sometimes telescopes might have issues with those, but at the moment we're doing quite well. And our telescopes are these big metal things, and so they're quite sturdy.
So that means that you can't just whip out your iPhone while you're doing your data collection in Australia, right?
Well, I can if I'm doing it remotely. Okay. So I don't actually have to go out to the telescopes all the time because, again, Wi-Fi, internet. Well, we don't use Wi-Fi at the observatory. Sorry, we use hard wires. But yeah, if I'm actually at the observatory, you're not allowed to turn on any mobile phone signals. You can't even have a Bluetooth or anything. Drones are out of the question. Those produce a lot of RFI. So all those things must be switched off, or else we don't actually get to do the science that we want to do.
Another question, if dark matter is so heavy and makes up so much mass, why isn't it at the center of galaxies?
That's a good question. So there is a lot of mass still in the center of galaxies. So a lot of that mass in the center actually comes from stars and gas. But yeah, there is actually kind of a dearth in the center. And so when we look at those rotation curves, we do see that that is actually a lower velocity in the center, and it actually moves outwards. And I think that's basically just how the universe formed. And so these halos formed first, and so all the mass was there, and then it pushed all the stars and whatnot into the center, and so that's where we have the centers. And so it's just where each part of the galaxy lies. And so we do have stars in the center, and then kind of gas more on the outskirts, and then dark matter on the edges.
Mm-hmm. So you showed a lot of really gorgeous pictures of galaxies, galaxies being my personal favorite as well. How are pictures of galaxies colored?
So we actually, so the ones that you saw in the starlight, they're taken using different filters, and then you just add them together. And so it's basically, you would take a picture just looking at the blue, let's say, and then taking a picture of just looking at the red part of it, and then you'd put those together. And so that's what we do. So technology nowadays with your normal camera, you can do that, right? But before, photos actually used to be black and white because you couldn't actually get all those colors, but now we can put those together. And so it's just, we look at it in different filters, and so we can get those colored images, and so those pretty ones with all the stars. And then we can always add in all the rest of the electromagnetic spectrum. And so it just depends on how you want to show your images.
And I always like to mention this radio is like its own weird breed of astronomy, because you get like power spectra, and then you need to do something wild like a Fourier transform to like get something visual on it, right?
Yes, I didn't want to scare them too much about that and all the mathematics involved. So yes, it's a bit technical, but again, I work with a lot of professionals. So we have computer programmers and software designers to actually make all this software and all these tools that I can use. So it's much easier for me.
Mm-hmm. So how did you know that this was something you wanted to go into? And was it hard to adjust to life in Australia? I know you used to have huskies. I don't know if you still have them anymore, but huskies in Australia, I don't really see that too well in my head.
I still have them. They're both here, Trooper and Echo. They're alive and well. So yes, they flew down from Canada all the way to Australia. They are more well-traveled than some of my family members. But yeah, so I realized I wanted to do astronomy from when I was a child. I did kind of veer in different directions, but I always came back to wanting to just look up and understand what's going on out there in the universe, like at the night sky. Like that was the thing that got me hooked. So every time I go out, I love looking at the stars. I love looking at planets and all those things. And so that has always brought me back. So even when I did all my other degrees, I was in the military, all that stuff, I would always go back to the night sky. And as for life in Australia, it's actually not too different from Canada. I showed you all the landscape that was similar, but politically, economically, it's actually very similar. The only two differences that I'd point out would be the weather is much nicer. So we don't have snow mostly down here. And today it was about 20 degrees, 25 degrees. Tomorrow will be about 35. So I'll probably go to the beach. Sorry if some of you are jealous. And the second thing that I noticed that was very different is the moon is actually upside down. So it's kind of rotated, but that's about it. Everything else is mostly the same.
Cool. So we'll take one last question. How are elements in stars identified from light years away?
So without getting into too much detail, so we have this thing called spectroscopy, but it's pretty much just how we look at how light reacts with different elements and whatnot. And so we can see, so the hydrogen gas that I actually look at, it peaks at a certain part in the electromagnetic spectrum. And so that, that radio frequency thing and so it peaks at a very specific frequency. So it's like tuning like a radio station, like in a car or something. You tune it to like an FM or AM or something, you tune it to a certain station, right? And then you know that that music station is playing whatever songs that you like. Well, we're doing the same thing when we're using different telescopes. And so we're actually tuning it to different frequencies and we're probing different parts. And so we know what elements or what molecules might emit, what frequencies that they're brightest at, and that's what we can tune to, and that's how we actually see what's in all these other extragalactic, stars and galaxies and all that stuff. It's by looking at very specific frequencies of that electromagnetic spectrum.
It's kind of crazy what we can do from so far away, really, with the technology. So that was all for the questions. Thank you so much again for that great talk. We're now going to take a quick health break. So you can get up, walk around, stretch a little bit, and we will be back at 1:55 Eastern. So that would be -3, that's 10:55 Pacific. So try to adjust for your time zone, but basically we'll be back in about 13 minutes for the next talk. Thank you so much. Hi, everyone. Welcome back from your break. I hope you had a sip of water, took a little walk around your place, had a stretch. So we're going to go on with our program now, and we are thrilled to introduce our second speaker of the day. If she is here. Perfect. Her camera is on. So Professor Nassim Bozorgnia. Professor Bozorgnia received her PhD from the University of California, Los Angeles, or UCLA, and is currently an assistant professor in the Department of Physics and Astronomy at York University. Her research is focused on understanding the distribution of dark matter in the Milky Way and its implications for attempts to discover dark matter. We are lucky to have her today to shed some light on one of the biggest mysteries of the universe. And a little fun fact, before she became a physicist, she also dreamed of becoming a pilot. She hopes to find the time in the future to take some flying lessons and pursue this dream in her free time. So I will hand it over to her now to kick us off on our dark matter journey, and you can go ahead and share your screen.
Okay, thank you very much. All right, so thank you very much for the invitation. I'm very happy to talk about dark matter today with you guys. So I'm going to focus on the dark matter distribution in our galaxy and how we can search for it. So let's start with a simple question at the beginning. So what is the universe made of? So all the atoms that exist in our bodies, in the planet Earth, in the sun and other stars and the different galaxies, these all make what we know as the ordinary matter. And as you saw in the previous talk, this ordinary matter just makes up about 5% of the energy matter content of the universe. 68% is in the form of this unknown dark energy, which is responsible for the accelerated expansion of the universe. And you'll hear more about it in the next talk, and 27% is made of this unknown dark matter component, which we're going to talk about a bit more. So if you just focus on the matter component of the universe, so just looking at this part, then 15% of it is in ordinary matter, and 85% of the matter content of the universe is in the dark matter component. So dark matter has not been detected yet. We have a lot of evidence for its existence, and all this evidence comes from its gravitational interaction with ordinary matter. But we don't yet know what is the nature of the dark matter. If it's a subatomic particle, what exactly is its nature? What is its mass or interaction strength with ordinary matter? Now, we have the evidence for dark matter from a variety of different observations and scales, basically from the scales of small dwarf galaxies to galaxies the size of our own galaxy, to galaxy clusters, and even to the largest scale structures of the universe. So let's just focus one more time, because of its importance, on this evidence of dark matter coming from galaxy rotation curves. And you heard about this in the previous talk, but just to go over it one more time. So this is the measurement which was pioneered basically by Vera Rubin and collaborators in the 70s. And you see here in this plot, the measurement of the rotational velocity of stars and gas as a function of the distance from the center of the galaxy. And based on the gravitational laws that we have, we would expect that as we go beyond where the visible galaxy ends, then this rotational velocity would just decrease. But what we actually observe is that as we go beyond the luminous part of the galaxy, there is still some rotational velocity, and actually it increases and then it flattens out. And so this is just telling us that there is mass beyond where we see the visible galaxy. And so there should be, this is an unknown form of mass that does not interact with electromagnetic radiation, and we cannot see it. And so let's ask the question of what does a galaxy look like? So this is the picture we have for a sketch of a galaxy, a spiral galaxy like our own, before the 70s, before these measurements of the rotation curves. But afterwards, we have a completely different picture for what the galaxy looked like. And now we believe that galaxies like our own are embedded in this large spherical halo of dark matter, which has a radius more than 10 times the radius of the visible galaxy. And so we call it a halo. It's just really a sphere, and it's filled up with, we believe, there are many models and theories for what dark matter is, but one of the prominent ones is that it is subatomic particles. And the density, I'm going to talk a little bit more about it in a few slides, but we have the density of dark matter being the largest in the center, and as we go to the outskirts, it just goes down as well. But just beyond where the galaxy, the visible galaxy ends, still there's a lot of dark matter here, and so that is why these rotation curves are flat. Now, this is not still the completely true picture of how the full galaxy with its dark matter should look like. If we could actually see the dark matter here, this is the more accurate picture of how the galaxy would look like. And this is a result of a numerical simulation of galaxy formation. And what you see here, so this is just the visible part of the galaxy, but all these little bright spots that you see are dark matter subhalos, so substructures of dark matter of different masses, and they are, numerous of them in the galaxy. So it's not just the smooth part of the halo, but there is also a lot of substructure, we believe, in the galaxy. Now, one of the other very important evidences for dark matter comes from the measurements of the cosmic microwave background radiation. So what you're seeing here is really a snapshot of the universe when it was very young. So this is around 400,000 years from the Big Bang, and this is the light that has traveled from that time, and it has reached us now. And the different colors in this map is just showing the different temperatures. So the orange is the hotter regions, and the blue is the colder regions in this map. And so to understand why this is really important and what it tells us about dark matter, let's just try to see what exactly the CMB is. So the CMB is really, as I mentioned, the oldest electromagnetic radiation in the universe. And around 380,000 years after the Big Bang, neutral hydrogen atoms formed. So before that, we had electrons and protons in the universe just flying around. And so photons, which are the particle of light, they were scattering around and they could not escape. They could not travel freely, basically. And around that time, when neutral hydrogen atoms formed, then photons could travel freely, and the universe really became transparent to photons. And this is really the radiation that we are receiving now. We are seeing this, this picture now from that early universe. And these photons really fill the entire universe today, and they give this almost uniform background. but there are still very tiny fluctuations in this background, and these are on the order of 1 part in 100,000 across the sky. So these are the fluctuations occurring in this background. And basically, this is very important because if we study in very detail the pattern of these fluctuations in this map that I showed you, then we will find this overwhelming evidence for dark matter, and it can actually tell us to the percent level the amount of dark matter in the universe. And so the percentages that I showed you in the beginning is really coming from this data from the CMB that we have. Now, we can use these percentages that we have for the amount of dark matter and the amount of the ordinary matter and actually simulate the universe and let it evolve from the time of the Big Bang until today. And these simulations have been running on supercomputers. And you see, I'm just going to show you one of these simulations, and you saw something very similar in the previous talk. This is the illustrious simulation showing you the dark matter density. So this is close to the time of the Big Bang, where the universe was more or less uniform. But now, under the force of gravity, dark matter clumps together. So you're just seeing dark matter here clumping together. And it forms basically these more dense regions where the different colors are showing, the white is showing the more dense dark matter regions. And these become really the seeds of the galaxies which would form later. So because of the gravity, effect of gravity, if you now consider gas, gas would fall into the seeds, and now it has switched to ordinary matter. Actually, you're seeing the different colors are different temperatures of gas. Gas fall into these gravitational potential of where the dark matter has clumped, and then it can cool and form stars, and then galaxies form basically. And so in the most active galaxies, also supermassive black holes form. And so you also see all these effects with the gas and the black holes and so on. But so you see the time actually here, this is about 6 billion years after the Big Bang. And if you let this kind of simulation evolve until today, so around 14 billion years after the Big Bang, you actually see multiple galaxies form. So this is just looking at the visible part of the galaxies. And you see that these are all simulated galaxies, but they look a lot like all the galaxies that we expect to have in our universe. So basically, dark matter is needed to form these galaxies. Without dark matter, we wouldn't have the galaxies forming. And so this is the picture of our simulated universe, which look a lot like the observed universe, and we need dark matter for that. So I mentioned all these evidences for dark matter, but what is the dark matter distribution in galaxy like a Milky Way, basically, in our own galaxy? So we have a theoretical model for this called the standard halo model, which also has been tested against data, observational data. And this is really the simplest model for the dark matter distribution in our galaxy. In this model, we have, as I showed you before, the spherical halo of dark matter. So these are collisionless particles making up this spherical halo. And just to show you the density of dark matter, so mass divided by volume of dark matter, as we go from the center of the galaxy to the outskirts, this density just decreases. So dark matter is densest in the center of the galaxy. But if you think about the dark matter, amount of dark matter in the solar system, actually that's quite low. So in particle physics units, and I'm going to tell you what this is, this is about 0.3 giga-electron volts per centimeter cube. And to understand that a little bit better, so the mass of the proton in these units are 1 GeV. And so this is about the mass of 1 proton per every 3 centimeter cubes. And in units that you're more familiar with, this is going to be a very, very low number. So this is about 5 times 10 to the minus 25 grams per centimeter cubes. So this is a 1 and 25 zeros in front of it, and then a 1 divided by that large number, right? So this is very small. And just to think how many dark matter particles we expect in a coffee mug, we only expect 1. So comparing that to all the subatomic particles, the amount of atoms we have in a coffee mug, this is really small. But indeed, there is still dark matter in the solar neighborhood, and we have ways to try to detect it. We haven't yet detected the particle dark matter, but we have a large program searching for these particles. And one of these programs, actually, experiments are in Snow Lab in Canada, more than one, but a number of these really cutting edge experiments are operating there and searching for dark matter. All right, so how do you measure the dark matter close to the position of the sun or in our neighborhood, basically? So one way to do this is to measure the vertical velocity of nearby stars, and this would tell us about the gravitational potential around the position of the sun. And based on that, you can relate that to the amount of matter around the position of the sun. And since we know how much matter we have in the ordinary matter, basically stars and gas, we can then deduce how much dark matter we have in our neighborhood. Another way to know how much dark matter there is to actually have a theoretical model for the mass of the Milky Way at different locations in the galaxy, and then also use the data from rotation curves, try to fit that data and try to deduce how much matter and how much dark matter and ordinary matter we have at the position of the sun. So actually, these measurements of the local dark matter density goes quite back in time, and it has a long history. This is a picture of the Dutch astronomer Kapteyn, where already in the early 1900s, he used these measurements of the velocity of stars close to the sun and estimated the dark matter density close to us to be about 0.285 GeV per centimeter cube. And after that, there were multiple measurements using various data sets. And the numbers that we have now all fall between 0.3 and 0.6 GeV per centimeter cube. These are all the recent measurements and considering the uncertainties in these numbers. So actually the measurements, this historic measurement by Kapteyn was not very off. It was on the lower side, but still it's remarkable that even in 1920, astronomers were able to make these kind of measurements of the dark matter density. So I've talked a lot about the dark matter density and this component in our galaxy, but what is a way to astronomically search for these dark matter subhalos that I mentioned? So actually, we have a very nice way to search for them. There are many ways, but I'm going to focus on one of them, which is really cutting edge research going on now. And this is using the data that we have. We can use astronomical data. This is the data that we have from the Gaia Space Observatory, which is this European Space Observatory. And it has produced really a revolutionary map of the visible part of the Milky Way, which you're seeing here. This is from the last final data, one of the last data releases of Gaia. And so what Gaia does is measures the position and velocities of stars in our galaxy. And it has already measured more than 1 billion of these stars, so the positions and velocities of these stars, and it has given us this really detailed map. So how can we use this to search for dark matter? Because here it's just a luminous matter, right? So we have all these positions and velocities. What can we do with it? So one way to search for dark matter is to look at something which is called stellar streams. So these stellar streams, which you kind of see them here, these are multiple of these streams, they form when you have a dwarf galaxy, a very small galaxy, which, or a globular cluster, which is a collection of stars. And they are disrupted and torn apart by the potential gravitational potential of the galaxy. And the stars are actually just put in these orbits, around the center of the galaxy. And so you see some of these streams here. And so how can these stars, or what can these stars tell us about dark matter? So remember that this picture actually of the galaxy, this is just the luminous part or the visible part of the galaxy, but this is embedded again in this large dark matter halo, and you have all these dark matter subhalos here. So you have all these stellar streams, and you have all the dark matter subhalos, and they can actually get close to these streams, and they can perturb and disrupt these streams a little bit because they interact gravitationally with the stars in these streams. And so you might see some perturbations or some gaps in the stars of these streams. And by studying these detailed effects in these streams, you can actually infer that this might have been due to some dark matter subhalo flying by. So I show you, just as the last slide, one of these, the actual data from Gaia, looking at one of these streams. So on top panel, you see the location of the different stars in one of these streams, the GD1 stream. And you see already some features here. So there are some gaps in this location of these stars and some features here. And if you take a smooth stream, which looks a lot like this, but everything is uniform, which is what we would expect from these streams. And then you simulate the effect of a dark matter subhalo with a specific mass going close by the stream, you would get this bottom panel plot, which looks very much similar to this top panel. And this is just telling us that, yes, it can be that the dark matter subhalos are causing these features in the stream. And so by the detailed analysis of all these stars in these streams, we can infer that this might have been due to dark matter. And we can actually see how many of these subhalos we have and how they're distributed in the galaxy. So just to conclude, so the evidence for dark matter comes from a variety of different observations. But we haven't detected dark matter yet. We still don't know what the nature of dark matter is. We have a lot of astronomical data to analyze, and we can use those data, plus the cosmological simulations we have, and to extract the dark matter distribution in our galaxy using both of these. And there are really large worldwide theoretical and experimental efforts on their way to unravel the dark matter mystery. So if you're interested to continue or in this field and start your studies in this, you might be part of a team which would ultimately discover dark matter. Thank you.
Thank you so much, Professor Bozorgnia. Yeah, lots of work to do. I think that's going to be a recurring theme during this workshop, that anyone who wants to do astrophysics later on, there's plenty of work to go around. So a reminder, if you have any questions for our speakers, you can use a Q&A feature. So we're going to start off with some questions now. What does being a professor in astrophysics look like with new information and data being collected all the time? How do you ensure content you're teaching is up to date?
It's a very good question. So I'm actually a theoretical physicist, but working in astroparticle physics. So not really an observational astronomer, but we use, you know, that you have to be definitely on top of all the data. And I have collaborators who work directly with the data. And you also have to be up to date. So, you know, the day-to-day life is that you definitely have to, you know, check all the new scientific papers which come out on this, go to conferences and keep up to date with you know, the different collaborations which are working and you're working with. And so in terms of how it affects the teaching, it's always interesting to, if you're teaching a course which is related to astronomy, it's always interesting to put in some new results that came out, or how it relates to your actual research. So it's really fun.
Yeah, it is a growing field and it's evolving very, very quickly. I know a lot of us, we subscribe to something called Archive, where everybody publishes their work. And every morning we wake up, we take our coffee, we look at our email, right, and we see everything that was published while we were sleeping. And so it can be pretty intense. How valuable is an astrophysics degree today? Does it allow for you to get a job in the field comfortably?
I think anyone who would go in this field should really love it. So for me, it's the passion which drives you to go and work in this field. And so when I decided to go in this field, I wasn't thinking, well, would I have a job at the end and how much money I would make and all these practical questions, because it was my love of pursuing this. But if you love it, I mean, I would say it's a difficult field in general, because there aren't as many jobs as you might find in other fields. But if you love it and you pursue it and you do your best, I would imagine that you would find a job in this field in academia. And then there's also a very a high probability that a lot of the PhD students in astrophysics and physics in general find jobs outside of academia, which are still very good jobs, and with data science or related jobs. So there's always with a PhD in astronomy, you'll have much better chance of finding jobs which are good jobs. So
I always like to say that a physics degree turns you into a problem-solving machine.
Exactly.
And so that can be in space, in the universe, or that can be with data science or tech or anything like that. So you become very, very good at solving problems in lots of different fields. You're very marketable as a PhD in astrophysics. Mm-hmm. How can students gain experience in this field?
So there are programs like this one, which is quite nice, I think, for high school students to join, and work in teams. If you do decide to continue and go to university for, in this field, as undergrads, you will have, even as first-year undergrads, and especially, in your second year, you'll have definitely a lot of opportunity to get hands-on experience working with professors, various opportunities to collaborate, work in teams. And so at York, for example, we have this program that we're just starting, and between a few professors at York with professors in Germany, and then there are students both from the German side and from the Canadian side. These are maybe first, second year students which will join and work on some topics which are real research, and it's quite fun. But as high school students, programs like this are very useful. I'm sure there are others which are similar, and you can definitely start thinking about these. There's also a lot of interesting YouTube talks you can go to just get more information. There are a lot of good books, I would say, so to just keep the excitement going.
Mm-hmm. And I always like to mention, if you do go on to do undergrad in physics, try to do research projects or internships as soon as you can, because research and courses and exams are absolutely not the same thing. They're very, very different. And what you end up doing later on is research, not exams. So it's a good test to see if you like astrophysics. Mm-hmm. What are some key skills that you need to succeed in related university programs or careers?
So these are the skills you will obtain. You don't have to have them at the beginning, and a lot of the students don't have this at the beginning, but when you go to university, you'll start obtaining these skills. Well, you should, if you really want to work in this field, you will obtain a lot of programming skills, coding skills. Then, of course, there's the theoretical part, which, as you take your courses, you'll learn a lot about the theoretical part. And mathematics, of course, is a very big part in all of this. And it's just as you take your courses, you learn those. So it's not expected that you can come with all these skills. It's just the first few years in university, which you'll find these, data analysis skills as you get into your research projects, and gradually you'll build up on that. So
yeah, no one is born knowing calculus.
Definitely.
You pick it up along the way.
Mm-hmm.
Okay, so a bit of an existential question now. What are some possible benefits of astronomy and astrophysics to life on Earth?
It's a very good question. A lot of the research that we do, you might think about it as curiosity driven. So we want to know our place in the universe. We want to understand what it's made of and all that, all those big questions. But there's a lot of benefits which applications basically which come out of it. Maybe they're not straight away, you might not think about them, but in the long run you would see that these applications actually come where you wouldn't have thought about it at all. So for example, a very famous example is from particle physics, the Large Hadron Collider at CERN, which is, in between Geneva and France, Switzerland, and France. The World Wide Web was actually born there. So it's just amazing to think it wasn't why this was built, but it was there which this was born. You can think of all the applications in, if you think about the medical industry, all the applications of physics that you'll see happening, in MRI devices and so on. With astronomy, of course, I mean, you can think of various things. For example, finding, we had a very interesting talk at York about finding asteroids. And so there are programs to try to figure out if there are asteroids which might hit Earth. And if we didn't have that knowledge of how to find them, we wouldn't even know if an asteroid, large asteroid, would be coming like the one that hit Earth and killed dinosaurs, for example. So, I mean, there are applications which you might not immediately think of, but at the end, always increasing our knowledge always leads to some very important things that you have to, consider.
Yeah, the example I always like to use is that the camera in your cell phone to take a selfie comes from astrophysics. So, you're welcome for all your selfies.
The GPS, you need the laws of gravity.
That's right.
Yeah.
All right, so we will wrap it up with that, but thank you so much, Professor Bozorgnia, and a really great talk, and lots of work to do. So we wish you the best of luck with the rest of your research.
Thank you very much.
So we're going to go right ahead with the final talk of the day. We've learned a lot about galaxies and dark matter up until now, but what other secrets does the universe hold? And it's a big secret that we have to tackle now. So I'm pleased to introduce our third and final speaker, Professor Celia Escamilla-Rivera, whose talk will round out our view of the universe. Professor Escamilla-Rivera received her PhD in Science, Technology, and Space Observation at the University of Basque Country in Spain. Currently, she serves as the head of the Department of Gravitation and Field Theory at the National Autonomous University of Mexico. Her research is focused on determining the structure and amount of dark energy in the universe. Although her first love is astrophysics, she is passionate about fencing and was very close to competing in the Olympics. So please welcome Professor Escamilla-Rivera in our final talk of the day, and I will leave the floor to her now.
Okay, so thank you very much for the invitation. I am glad that everyone here is interested in the big dark side of the universe. So part of my talk will be in the direction of a study and understanding what's happening with the bigger sides of matter in the universe, matter energy, in this case, the dark energy. So let us start first with something very simple, physics. Physics is a huge subject that covers many different topics, going from galaxies in the deep space right down to subparticles. And if you don't already know physics, it is difficult sometimes to see how all these different subjects are related to each other. So physics can be broadly broken down into three main parts: classical physics, quantum physics, and relativity. So to understand how important are these three areas to understand the universe, let us begin by winding the time-like bound back to 13.7 billion years, to the beginning of time. So imagine that we are going forward to this point and then something happens. Around us, there is nothing. There is not either time or space. Imagine the darkest empty thing you can and cube it in a gasoline times, and that is where we are. And suddenly, bang, a universe appears, an entire universe. And we have crossed our first thresholds. The universe is very tiny, it's smaller than an atom, and it's incredibly hot. So it contains everything that is today universe. So you can imagine that it's bursting and it's expanding at incredible speed. And at first, it's just a blur. But very quickly, distant things begins to appear in a blur. So within the first second, energy itself shatters into different forces, including electromagnetism and gravity. And energy does something else quite magical. It congeals to form atoms and quarks that will create protons and leptons that include electrons. And all this happens in the first second. So let us now move forward until 380,000 years. That is twice as long as humans has been on this planet. So now simple atoms appears in type of hydrogen and helium. So now I want to pause for a moment. In 380,000 years after the origin of the universe, because we actually know that quite a lot about the universe at this stage, we know about all is extremely simple. It consists of huge clouds of hydrogen and helium atoms, and they have not a structure. So they are really like a sort of cosmic mush. So that is how it works. Gravity is more powerful where there is more stuff. So where you get slightly denser areas, gravity starts to compact clouds of hydrogen and helium atoms. So we can imagine the early universe breaking up into a billion of clouds. And each cloud is compacted, gravity gets more powerful and density increase. And the temperature begins to rise at the center of each cloud, and then at the temperature what crosses this threshold temperature around 10 million degrees, protons start to fuse. And there is a huge release of energy, and bam, we have a few stars. And from about 200 million years after the Big Bang, stars began to appear, and all through the universe, billions of them. And you can also need a great diversity of chemical elements. So you will need liquids as water. And the universe now significantly is more interesting and more complex. So the next question is, looking at the sky, we are amazed by how it seems to go forever. But what will the sky look like billions of years from now? So that is why we have not only machines and technology at the Earth, we also have the capacity to send some ships to the space. So a particular type of scientists, called cosmologists, spend their time thinking about the very question. So the end of the universe is intimately linked to what the universe contains. So over 100 years ago, Albert Einstein developed the famous theory of general relativity, formed of equations that help us to understand the relation between what our universe is made of and its shape. It turns out that the universe could be curved like a ball of sphere, like we are seeing now, but we call this universe positively curved or closed. But another idea is that it could be shaded like a saddle. So we call this negatively or curved or open universe. So the most simple that we can know about the universe is that it could be flat. So at that shapes determines how the universe will live or die. And we know that the universe is very close to flat. So however, the components of the universe can still affect its eventual fate. So we can predict how the universe will change with time if we measure the amounts of energy densities of the various components in the universe today. So the next question is, what is the universe made of? So the universe contains all the things that we can see, like stars, gods, planets, animals, and so on. So we call these things ordinary or baryonic matter. So even though we see them all around us, the total energy density of these components is actually very small. It's around 5% of the total energy of the universe. So now let us talk about another percent of the universe, the 95%. So just under the 27% of the rest of the energy density of the universe is made up of what we call dark matter, as we saw in the last talk. So dark matter is only very weakly interacted with light, which means it doesn't shine or reflect light in the way that stars and planets do. But in every other way, it behaves like ordinary matter. It attracts things gravitationally. In fact, the only way we can detect this dark matter is through this gravitational interaction, how things orbit around it and how it bends light and skews the space around it. So we have yet to discover a dark matter particle, but the scientists all around the world are searching for this elusive particle or particles and the effect of dark matter on the universe. but still doesn't add up to the 100%. The remaining 68% of the energy density of the universe is made up of dark energy, which is even more mysterious than dark matter. So this dark energy doesn't behave like any other substance that we know and acts more like anti-gravity force. We say that it has a gravitational pressure which ordinary matter and dark matter do not. Instead of pulling the universe together, as we expect from gravity do, the universe appears to be expanding apart and even increasing rate. So at this point, we have a part of normal matter, a considerable dark matter, and an incredible quantity of dark energy, where the dark invisible things remains to know. The leading idea of dark energy is that it's a cosmological constant given by this letter that you can see now in the screen. So that means it has the strange property that it expands as the volume of the space increases to keep its energy density constant. So as the universe expands, as it's doing now, there will be more and more dark energy, and dark matter and baryonic matter, on the other hand, don't expand with the universe and become more diluted. But because of this property of the cosmological constant, the future of the universe will become more and more dominated by dark energy, becoming colder and colder and expanding faster and faster. Eventually, the universe will run out of gas to form stars, and the star itself will run out to full and bored of leaving the universe with only black holes, as we can see in this simulation. Given enough time, even these black holes will evaporate, leaving a universe that is completely cold and empty. So that is what we call the heat death of the universe. So we are coming back to the first point where we started. So what's happening? Well, it may sound some depressing to living in a universe that will end its lifetime cold and devoid of life. The end fate of the universe actually have a beautiful symmetry to its hot and fiery beginning. To reveal its nature, we have technology and data at hand. As we can see in here, we have huge telescopes in Earth to look as or to form like eyes to expect or at least to observe the universe. So what happened with the data? The data is around us. So as you can see in this plot, there are many data in every application that we have at hand. Just to give you an example, if you can see several videos, for example, in a platform like this YouTube, you will have at least a contact with 25 bytes of data per day. That is more or less, if you multiply in this quantity by 10 to the 12 number. So it's a very huge number. So imagine there is a very huge laboratory in Europe called CSIRO, as we can see in here, and the same produces around 15 petabytes. That is around a number that is multiplying by 10 to the 15. So it's more bigger that we can use in related to the videos that we download from YouTube. If you want to compare the data with this laboratory in Europe, you will need to reproduce around 200,000 times several videos per person in the whole world. So imagine the quantity of data that we have at hand. So what kind of data we can recompile from these several experiments, not only in the Earth, but also that we have in space? One of the most interesting are, for example, these pan-stars, the Panoramic Survey Telescope that is now located in USA. So this kind of telescope have the capacity to have a reservoir around 2 petabytes. So it's quite a huge number of data. Just to give you an example of how it works, this telescope, you have around at least this telescope detected around 2,000 just asteroids that came very, very close to the Earth. So this is one of the purposes of this mission. Another very interesting missions in the Earth is the Square Kilometre Array that is located basically in South Africa, but have some collaborations in Australia. So this array of big antennas recompiles around 700 terabytes. So imagine the large number in comparison to parent stars. Another mission that is going to be in the space very soon is the Euclid. Euclid Consortium is from parts of the Europe, and this kind of apparatus is going to recompile millions of terabytes. So it's nothing compared with what we have on Earth. Another interesting that is very related to the looking for the dark energy is the dark energy spectroscopic instrument. This is an array of 3 telescopes, not only in USA, but also in South America, that is going to compile millions of petabytes, and not only data, is going to produce the first 3D map of the universe. So imagine now we have now a full photograph of the entire universe. So at the end, what we are measuring for this kind of apparatus. So just now, somewhere in the universe, a star exploded. In fact, a supernova, a type of a star, occurs every second or so in the universe, or in the observable universe. And there is one on average every 25, 50 years in a galaxy the size of an age of the Milky Way. So many years ago, 2 teams of astronomers that compiled, for example, persons like Cyril Permuter, Brian Smith, and Adam Rees, were using the world's biggest telescope to peer as deeply as they could into the universe. So they were looking for incredible distant supernovae, and not only just any kind, but an special ones called types 1A. So they occur when a white dwarf increases in mass until electron degeneracy pressure can no longer sustain it and against its own gravity. It collapses, undergoes a catastrophic wave of thermonuclear fusion, and explodes. So from here, the luminosity of these stars are unknown. Plus, measuring how bright they appear to be in a telescope, we can calculate their distance from us. So this can tell us how fast the universe is expanding on really big scales, and this expansion is speeding up day, and the reason of this behavior is the famous dark energy. So most of the cosmologists have concluded that the universe contains more than meets the eye. Observation of pinwheeling galaxies suggests that there is skyfalls of invisible matter held their stars together, while a repulsive photon eternity drove galaxies apart. Experiments like Planck collaboration has spent years collecting microwaves coming from all directions of the sky. So this kind of data is known as cosmic microwave background radiation. So by snapping this a photograph of the young cosmos, we can peel down its age and its shape as well, and determine how exactly how much dark matter and dark energy contains. Dark energy, meanwhile, played a negligible role in the universe's youth, in presence that it can be inferred from CMB, indications that the universe is flat today. So the measured quantity of dark and visible matter just don't have the muscle to flatten the space, but adding dark energy to the modern universe and everything balances. So one day in the future, we hope to close all these topics in physics and solve the major pulses of dark matter and dark energy. So we live in an extraordinary time in the life of the universe, so we can start to understand the universe journey and view a history that plays itself out of the sky for all to see around. So thank you very much for this invitation.
Great, thank you so much, Professor Escamilla-Rivera. Now we're going to go back to some questions again. Again, if you have any questions, the Q&A feature is there for you, and we're going to jump right in. Could dark energy be one of the key accelerants to what caused the initial expansion of the universe?
Yes, indeed. In fact, dark matter, well, in this case, dark energy have a lot of phases. For example, you can design an equation like a parametrization. We call this, in the theoretical cosmology, call this a parametrization of a form of a fluid. So if you consider a fluid that has a negative pressure, that is very interesting because in the nature, we don't have anything that have something like is negative. So it's very impossible to think, oh, we have a negative fluid that can push that all this is around us. So this is possible, and for now we have only a mathematical form of this kind of dark energy.
So I'm pretty excited about this next question here because the geometry of the universe is always very hard to address. How can the universe be flat if it's expanding outwards in all directions?
Indeed, that is a good question. I mean, it's not that the universe per se is flat. Is geometry. So that is quite interesting because everything in the universe is around matter, and matter curves the universe. So it's not like you can see it, and there is it's a good approximation of an example, but it's not the universe per se. Imagine that you have like a sheet, And you say, okay, this universe, it cannot be. I mean, I can notice something happening behind this. So it's not the form, but it is the geometry, and the geometry have a lot of things inside. So it's like, okay, we can think in a very summarizing form. You have something like is quite flat, but it's not per se the form. It's just the geometry, and per consequence is the quantity of something called the density curvature of the universe.
So you mentioned the heat death of the universe, which seems a little bit grim. And at the very end, we'd only have black holes who would themselves evaporate. So how does a black hole evaporate at the end of the universe?
Yeah, well, as all stars, I mean, the black hole starts to like suck it out of all the things that are around of these monsters in the universe. But at the end, there is enough energy inside of them. We don't know what is happening. This is something theoretical. I mean, it's just like fictional, but we hope, we see that if there is energy inside of this black hole, this energy is like the machine, the heart of the black hole. So at some point, this energy is not going to be enough to have an eternal life. So it starts to evaporate. The first person that established the equation for this phenomena was Stephen Hawking. Stephen Hawking said something is happening inside of these very huge monsters in the universe that it cannot live forever. So one way to this black hole starts to erase from this big universe is evaporate his own energy. So you can see this like the finish of the heart of these kind of monsters.
Nothing is eternal, not even black holes, sadly.
Exactly.
So you mentioned sort of the beauty of the symmetry between the beginning and the end of the universe. After the death of the universe, will there be another Big Bang?
That is a very nice question. I love it. This is one of my theoretical works that a lot of my students are now working out. Yes, indeed. I mean, it's possible, not experimentally, but imagine if there is something that starts with a point, the next step, okay, we will not finish this with another point. That is the beautiful symmetry. So there is a very popular models in cosmology called it the big bounce. It's like we are going from a big bang, a big crunch, and this can be eternal because it's possible to recover energy and lose energy. So it's part of the of how the universe can be works. But we have only equations. We have only theory around these things. Another interesting thing is that if there is black holes in the universe, there should be something different, or at least something that can produce an equilibrium between a black hole. If something that a black hole can suck things, there should be the contrary of black hole. So there is something called the white hole. So a white hole not suck the things, this like make a repulse function of that. And the connection between these two, the black hole and the white hole, is a wormhole. So basically, with this machine of the wormhole, we can make the connection between two kind of universe difference. So we have now like an imaginary or fictional thing that we can transport from a universe to another universe. So this point is like a cyclo. So when cyclo universe exists, there is a lot of equations. And of course, I mean, if we have now data and experiments in the space, why not look for something like wormholes in the space?
Mm-hmm. But that's all theoretical for the time being.
Yeah. Yes,
and the realm of science fiction.
Indeed, but it's very quite interesting. But yes, it's just mathematics, indeed.
Mm-hmm. Okay, so you mentioned black holes, which is always, everybody wants to know more about black holes. So can you comment on the importance of the first picture of a black hole that came out in 2019?
Indeed, I can comment very closely because I am part of the AHT collaboration, so good to know. So it's quite interesting. For the first time, it is possible to have a photograph of a black hole, but in some way it's not, and we need to be careful with this, it's not per se a photograph. We have the photograph of the first phase of a black hole. We call this part of the horizon of the black hole. So it is possible that now we can see practically an object that is impossible to see a naked eye. So this is, I mean, it was a very huge process, a lot of data involved just to have the first photograph. So it's kind of interesting because this is open a new door to analyze another kind of data. For now, we have data only from light, and also we have this CMB data recopilated from the beginning of the, well, very, very close to the beginning of the universe. But now we have data from something very interesting, black holes. And if we can take a photo of the horizon of a one black hole very near to us, it is possible that in the future, in many years ago, will be possible to take a photo of a very primordial black hole. And primordial black hole have data of precisely the Big Bang, of the possible Big Bang and the origin of the universe. So it's a first step in this career of the astrophysics and also cosmology to see how we can deal with data.
Wow, that's really fantastic. And yeah, we're seeing all these different ways to study different objects. It's sort of, we talk a little bit about multi-messenger astronomy now, where we have gravitational waves and we're studying particles and all different kinds of light to study all the different kinds of objects up there. So super exciting.
Yeah.
Another question now, will dark energy eventually cause the expansion of the universe to travel faster than the speed of light? So to expand faster than the speed of light?
Wow, that is a good question. I mean, there are very theoretical questions. In fact, it can be possible. But I mean, for now, the simple thing, I mean, the most simple things in physics are the most well-tested theories. In this case, for example, imagine that dark energy have a very particular mathematical equation, and this equation is equal to -1. If you set a -1 in the energy of this dark energy, you give this phase to dark energy, you will have a theory that is called lambda CDM. Lambda, this constant that I put in one of my slides, and then you combine this lambda with something called dark matter. So this is the most simplest model in cosmology that is very well tested with observations. So you will need here a value of -1 for this cosmological constant. But the next question is, what will happen if it's not a -1? Probably it's something different, something that is related to a quantity, related to the distance of an object. And this relation can give you a possibility, I mean, it's theoretical at this point, but can give you a possibility to travel faster than light. But you are violate all the laws of physics. So you will need to rewrite all the laws of physics just to adapt that kind of energy. And then you can make travel of times for sure. But this is just theoretically, but yes, indeed, is a possibility, at least at mathematical level.
Mm-hmm. Is there a lot of quantum physics involved in the study of black holes?
Indeed. Yes, there is a lot, precisely because we don't know what is happening inside of the black holes. So we need to compare, as you can see in this map in the picture, there is a lot of physics that involves to develop the nature of an object in the space or in the universe. So imagine that you want to understand gravity with something related to electromagnetism, something related to the weak force, to the strong force. So you need to unify these four forces, and the only way to do this is to unify something at cosmological scales and something in small scales. So to do this, we need quantum gravity. So it's quantum plus gravity at cosmological scales. So in this case, yes, there is a lot of studies. Black holes are like the right name of the black holes is compact objects. So compact objects is the first signal, and you can check if it is possible to unify things. Because as I mentioned, if the black hole sucks everything, so something is happening inside. So you need this unified theory. You need a quantum gravity to explain what is happening inside of these weird objects in the universe.
Yeah, because there's a bit of a crisis in physics right now, because we have gravity on one side, and that has to do with things that are very heavy, very large. And then on the other side, we have quantum physics, which are things that are very small. And usually those are like mutually exclusive. So things work out pretty well. But black holes are simultaneously super heavy, super massive, and like very small. So the two laws of physics need to work together properly. And yeah, they don't necessarily.
Yeah, indeed.
Yeah. Okay, dark matter being matter, does it have states of matter, or does it have different properties compared to regular matter? Perhaps they mean the fact that regular matter can be in a gas phase, liquid phase, solid phase, but dark matter, does that have different states as well?
Yes, well, we don't know. I mean, in some way, there is something theoretical models, because at the end we are looking if a dark matter can be a particle or maybe a group of particles. So there is a very interesting theory that combines a new stage of matter. In this case, is the Bose-Einstein condensates. So Bose-Einstein, if I'm not mistaken, a few years ago, it was one of more of the states of matter. We have liquid, we have gas, and also we have solid, but now we have condensate, Bose-Einstein condensates. So there is a possibility that dark matter can be a Bose-Einstein condensate. So it can have this something properties better related to the matter that you can know, but maybe we can explain this when we understand better this galaxy curve that we saw in the last talk.
All right, so we'll wrap it up with one more question. If the amount of dark energy is increasing in the universe over time, doesn't that violate the conservation of energy?
Well, there is a compensation in that. Remember that not only one matter is stopping the percent of the universe. The other is increasing, but the other are down. So we don't need, we are obeying the conservation of the energy at least a percent scale. But yes, indeed, we are violating all the kind of the properties of matter, because we are looking something that have negative pressure. Negative pressure never is going to satisfy the conservation of energy. So we need to restructure this equation and check if it's possible to have this in the future. So we have two phases. We need to compensate the 100% and then check if everything in conservation law of energy can be solved.
Great. Well, thank you so much for the talk, Professor Escamilla-Rivera. That was really, really interesting, and like so many mysteries. Dark energy is always a doozy to try to explain, but always super, super interesting. So thank you. Yeah. So those were our 3 talks for today. We're going to head to a break right now, the last break of the day. But before we do so, I just wanted to give a quick shout out to our 2 volunteers, Matthew and Yilda, graduate students at Queen's University, and they have been very diligently and very knowledgeably answering your questions in the Q&A, all the ones that I'm not asking verbally. So yeah, they've been doing a really, really great job. Keep sending your questions. They love answering, and they're doing a fantastic job doing that. So we'll go ahead with one more 15-minute break. So we will be back at 3:10 p.m. And then afterwards, we'll be doing a panel with our 5 student panelists. So yeah, walk around, take a break, go take a sip of water, and we'll see you back in 15 minutes. All right, welcome back from our break. I had a cookie during my break. I'm very happy about that. I hope you had a good break as well. So we're going to round out our first day of Let's Talk Astrophysics with a panel of current astrophysics students. They're thrilled to share all their tips and tricks about university, getting involved, and potential career paths. Again, as before, you can submit your questions to them through the Q&A function in Zoom. So I'm going to turn it over to our panelists, but before we jump to questions, I'm going to have each panelist introduce themselves. So to the panelists, please tell us your name, your program, a little bit about your science interest or research, and for fun, maybe one cool science memory that you have. So we can start with Martine.
Hi, everyone. My name is Martine Loken, and I'm a PhD student at the University of Toronto. For my undergrad degree, I went to University of Virginia in the US, and currently I'm studying cosmology, in particular studying the large-scale structure of the universe, of which there is a sort of simulation image in my background. As for a cool science memory, in my summer after my third year of undergrad, I got to go to Hawaii to do a summer research internship. And there I got to go up the mountain, Mauna Kea, and spend some time at the observatories there. And that was a really special experience.
Very nice. Yeah, always nice trips when you do astronomy. So next up we have Karen.
Hi, everyone. My name is Karen Macias Cárdenas. I'm a master's student at Queen's University, studying astroparticle physics, especially dark matter phenomenology. I did my undergrad in Mexico, where I was born, at Universidad Autónoma de Baja California. And a cool science memory that I have is that I got to do an internship in Copenhagen at the Dark Cosmology Center. And so that was really cool.
Very nice. Next up, we have Annika. Oh, you're muted.
Oh, sorry.
That's okay.
Hi, my name is Anika. I'm in my 4th year of an astrophysics specialization at Queen's University. I hope to kind of go on to grad studies and perhaps a PhD in the future. A cool science fact about me is maybe 2 summers ago, I volunteered with the Girls Camp through Snow Lab and the McDonald's Institute. And as a part of kind of our training workshops, we got to actually visit Snow Lab. So kind of put on all that mining gear and went underground. So that was really amazing. But yeah.
Super, yeah, Snow Lab, a super interesting place to visit. Up next, we have Ashley.
Hi, I'm Ashley Makuta. I'm an undergrad in physics at Queen's University, and I'm currently studying dark matter. That was with my summer job. And one cool memory I have was the same as Anika's, where I got to go to Snow Lab over the summer, and then I got to do a collaboration with them this year, which was really cool for me.
Awesome. And then last but not least, Catherine, would you like to introduce yourself?
Hi, my name is Catherine, and I'm also in my 3rd year of an astrophysics specialization at Queen's University. And I also hope to go on to do grad studies and maybe a PhD. And a cool science memory that I have is last summer, I also did some research, and it was focused on galaxies and trying to map dark matter within galaxies. So that was a really cool experience.
Cool, awesome. So the way this will work, we'll have questions coming in. If you feel compelled to answer that question because it really speaks to you, just go ahead, jump in and do that. Otherwise, I'll just go randomly between the different panelists. So we can start off with a question. Do required courses for undergrad physics programs have to be taken in day school, or can they also be taken in night school or summer school? Does anyone have any experience in night or summer school?
I can maybe speak a little bit about that. I was able to take a math course that was required over the summer, but I'm not sure, at least specifically at Queen's, they don't offer too many physics courses in the summer. So I think those are usually taken in day school.
Yeah, sometimes the astrophysics courses are a little bit more specialized, which is one of the nice things actually about the physics program. It's a lot smaller than like biology programs or med programs where you have like hundreds of people in an auditorium. Usually the physics programs are a lot smaller, but that means that there can be some more constraints related to the coursework that you have to take. All right, what does a typical day look like as a student or as a researcher? So I think that this is something that's relevant for everyone. So I'll let you all take a stab at the question. Martine, did you want to start?
Sure. Yeah, so at this stage in my PhD program, I'm done with classes. Typically in PhD programs, you do classes in your 1st and possibly your 2nd year, and you can continue to take some coursework if you want further on, but after you pass some qualifying or comprehensive exams, you're basically on to just focusing on your research and teaching. And so a typical day for me, if I have any teaching assistant work that day, might include running a tutorial for an undergrad course or responding to student questions online. These days, of course, it's all online. And in terms of research, a typical day involves a lot of computer programming for me. So I do a lot of analysis of simulations, I run simulations, and I also compare that to real data. And pretty much all of that is done mostly in Python on my computer.
What about you, Karen?
Right. So I just started my master's this year. And, the online thing may be a little bit different. But the usual way that I spend my day is between TA, teacher assistantship, research, and my courses. So I'm still taking courses because I just started my master's. So it's between those 3. But specifically, I think, of course, the part that I personally like the most is research-based. And right, because I'm starting my project, I'm trying to decide exactly what's it that I'm going to do with that. So I'm trying to, get myself a little bit into what's dark matter and the cosmology of it, the physics and the background, and then try to decide, what is a specific line of research that I want to pursue with that.
Mm-hmm. What about you, Anika?
Hi. So I'm still in my undergrad, so I'm in a full course load. I have 4 physics courses this semester, and I'm also in a chemistry course. And a typical day for me actually looks, I spend most of my time on Zoom in synchronous classes. A lot of physics professors do choose to run more synchronous class, as it's the easiest way for them to answer all of our questions and kind of explain the material to us effectively. And in between Zoom classes or after my day, I typically like to review notes, work on my problem set. And as an undergrad student, I also try to keep on top of my other extracurriculars and be involved at the school. So I kind of do a number of things all day.
Busy, busy though. You keep yourself very busy.
Yes, I am someone that likes to be very busy.
Good, that's good. What about you, Ashley?
I think, again, Anika kind of summarized it.
She scooped you again.
Yeah, as far as a lot of our classes are synchronous, and then so we kind of spend the day on Zoom right now, and then work on any assignments we have that are due that week. But I think as far as like also doing research during the semester, although I'm obviously a lot more focused on my school right now and my courses, but I still am able to do some research. So I usually do that on weekends, and then I'll meet sporadically throughout the week with my research group to make sure that stuff is still continuing along with our research to help us make progress during the school year, so then we can make a lot more progress over the summer.
Mm-hmm. And to round it up, Catherine.
I would say my day has probably already been summarized very closely by Anika and Ashley, but a lot of our courses are kind of in the morning throughout the day right now, so definitely spending most of that time on Zoom and then taking a break to make some dinner, spend some time with my housemates or my family, depending where I'm living, and then hopping back on Zoom and trying to work through some problem sets with my friends while still getting a social aspect, which I'm definitely missing out on right now from how school used to be. But yeah, that would be just an addition.
Mm-hmm. And I do want to point out that we're all in this pandemic right now, which is very unusual, but we won't be in this state forever. And I know in my experience when I was a physics undergrad and grad student, the community is really, really great. You're very close to your classmates. You rely on them to do your homework and pass your exams and not lose your mind. So it's really nice when you can actually work with them. So that's really good. All right, so I'll open it up to whoever is interested in the next question, which is, what's the coolest thing about your university and or your field of study? You can just like maybe raise your hand if you are interested in jumping into that. Sure, Karen.
Yeah, so as I said, I did university in Mexico, and then, now I'm in my master's at Queens, which has been online. But when I was an undergrad, probably the coolest thing was the kind of freedom that I have to choose my classes. Because when you're in high school, it's kind of like, well, these are the classes you get, and maybe you have like 1 or 2 electives. But when you're in university, and you also have some core classes, but there are way more electives that you can take. So you can expand kind of like your field of knowledge. So that was kind of like the coolest thing that I had. And about my field of study, which is astroparticle physics and cosmology, is that a lot of things are unknown, as we saw in the, in the talks. So there's a lot to learn from that. And, you can kind of test these crazy theories with the actual data that we have from observations and see if they match. I think that's a cool part of the study of it.
Awesome. Did anyone else have a different answer? Martin, I see you tentatively. Yeah, go ahead.
Sure, yeah, I can address this too. So one of the coolest things about university for me in undergrad and in grad school, but I'll focus on undergrad, was the opportunity to make friends with students who were interested in the same things as I was. And of course, in university, you make friends with lots of different students in lots of different fields, and that's great. But it's really fun when you get to, lab courses, or maybe an upper level astronomy course where you get to go and actually do some observing or run through some data. When you're, when you get along well with your classmates and you're working together to solve problems collectively, it can be really, really fun. And so I want to emphasize that because I maybe our previous answers talking about Zoom, where it didn't sound like it was that fun, but in normal times, that opportunity to work with others who are just collectively excited about the same things, and to get in interesting conversations about physics and cosmology and debate with your friends, but have a good time with it, is really special. And I think that's something that you have less of in high school, because probably not many people at your high school have the same exact interest of what they want to go into.
Mm-hmm. Very good point. Did anyone else want to jump in on this? Yeah, go ahead, Anika.
I think one of the coolest things that I found about Queen's is our professors, especially being in like an astrophysics specialization and that interest in astroparticle physics or particle physics in general, whatever your interest may be. Our affiliations are so close to Snow Lab, and a lot of the professors work on various projects regarding dark matter and particle physics. And the best thing about it is that they love talking about it, whether it be lectures or you go to office hours, anything like that. And they're always willing to kind of discuss their research, how they got into their research, how you could get involved. So that's like an aspect that I've really enjoyed about the tighter physics community at Queen's, is really getting to know my profs and being able to make those connections.
Yeah, that's a good point. It's a really good community. I'm biased because I went to Queen's, obviously, but yeah, it's a great community. Okay, the next question: how do researchers get paid, and how much do they get paid? So you can speak a little bit about, as an undergrad, as a graduate student, or if you have information even beyond that, go ahead. So I don't know if anyone feels compelled. Maybe the grad students can start. Sure, Karen, go ahead.
Yeah. So this is an interesting question because I feel like a lot of people, especially international students, don't know that some universities, when you do your master's or your PhD, are paid, which is a very good point, because, you know, people don't have like the means or the money to get into a PhD position, but, you know, if it's a paid position, well, that changes, that changes everything, which was my case. So the way that you get paid when, usually when you do a master's or PhD, in the States or in Canada and in some other places, is that you have to TA, you have to be a teacher assistant. So you count as an employee for that part, and you get paid for that part. And you also get paid for your research. So those are like your two sources of funding. And usually the way that it works is just that you get into the program, or you contact an advisor beforehand and, you know, ask around if they have funding for new students for the next year. That's kind of how it works.
Go ahead, Martine.
Well, I can just add, so it depends on which program you go to in terms of whether you need to find an advisor right away in your graduate degree who will be responsible for your funding, or whether you can try working with different potential advisors and not have to worry about the funding. So yeah, some programs you do need to have the advisor set up ahead of time, and you know that that's where your funding stream will come from. But for a lot of programs, it's a really steady stipend and it's guaranteed. And so even if, you know, in your first year or even 2 years, you're still figuring out what kind of research you want to do and who you want to work with, you will still get the same payment. And I think it varies, but if, you know, people want to know sort of how much, I think it can vary from in the 20,000s to 30-something thousand range in grad school. And around here, you know, that's definitely enough to live on. It's probably not enough to support a family, so that can be a struggle for some graduate students who have, you know, other people that they're responsible for. But often grad schools might have, or grad programs might have, additional support available for students who have, you know, those kind of external concerns as well. So it's pretty livable. And I would say for most grad students, the finances are not a huge concern. They can be part of a concern, but you can usually make it work.
Did anyone have any, yeah, Catherine, maybe undergraduate research funds?
Yeah, so last summer I was working under an NSERC USRA award. So that's an undergraduate student research award. And so NSERC supports the school in paying kind of your salary for the summer. And so I worked for 4 months, and at the end of each month, I got just over a $2,000 stipend. It depends on the year you're in and the school you go to. But that was my experience, and I found that to be enough to support through the summer and then pay for my education throughout the year.
Yeah, there are a lot of good opportunities. And physics is one of the better domains to get payment while you're a student as well, which is nice to know. All right, next question. And I'll send this maybe to Ashley. How is university different than high school?
That's a really good question. I think definitely like course-wise and class-wise, I feel like at least in first year, the classes do move a lot faster. So you'll cover a lot of the content that you would take like in a month in high school in like a couple weeks. So you like really have to stay on top of things, and you don't really have tests and stuff as much to like keep you on top of the content. So you're a lot more responsible for making sure that you understand it, and kind of like going out to look for help if you need it, like before an exam or something. But I think the class structure is also more fun in a way, because I think you have a lot more like demonstrations, at least in physics. Like we had way more demonstrations in physics in a week than I ever did like in high school. And you get to talk to people a lot more in class and work with other people. And I think you also get to like meet a lot more people because you're in a bunch of different classes. So it's not the same people in all your classes, where in high school they're a little bit smaller. So there's definitely some good and bad things, but I think overall it's just a great environment in university classes for sure.
It gets closer to like having a real job. You're more independent, so you have to self-motivate, but it's less learning things by heart and more applying things to real life situations, which is nice.
Yeah, for sure.
Yeah. Astrophysics is a vast field. How did you choose a topic to focus on in your studies or for research projects? Anyone? Sure, Karen, go ahead.
Yeah, so this is a great question. First of all, in my undergrad, I did physics, general physics. So I wasn't close-minded in the sense that I wanted to only do maybe astrophysics. You know, it was like, okay, that's what I like, but maybe I would like something else later. You know, and the sciences are now very interdisciplinary. So the way I began to explore physics was to go to research internships. The first one I did was in cosmology in Universidad de Guanajuato, working on dark energy, which Dr. Celia explained in the last talk. And then I went to MBI in Copenhagen to work with high-energy astrophysical neutrinos. And, you know, those were very different because one was like very astrophysical related and one was like early universe cosmology, but I liked both. So I was like, okay, what combines both of them? And so that's how I discovered like astroparticle physics, and how I ended up, you know, searching for masters that did astroparticle physics in the end. But it's definitely, I think the advice I will give is don't be close-minded. You just try a little bit of everything and see what you like.
Yeah, definitely. That's what the undergrad is for. You have multiple summers, so multiple opportunities for different research internships and different topics. Did anyone else? Yes, go ahead, Ashley.
Yeah, I think building off that, for me, I finished my second year last year, so that was kind of the first year that I was looking for a research job. And since it was my first one, I didn't have a lot of experience. Kind of the first one I could get, I took, because I was really happy to just get one. But that now is letting me have the opportunity to be a bit more particular about the job I'm getting for this year, because I have some research under my belt and I know what I did like and what I didn't like about it. So it's also, I think, important to keep in mind that the first one may not be your favorite, but I think you learn a lot about what it's like to do research, and then that will help you to figure out what you do like.
Mm-hmm. Are there any other thoughts on the topic? Sure, Anika.
Going back to kind of like course-based stuff for a lot of people choosing courses, I think something unique that really drew me to Queen's was the fact that it's more of a specialization. So Ashley, Catherine, and I are in the same program, and we take one astrophysics-based course every year. But along with that, we're still in courses like quantum mechanics. When you get into upper years, you get to see lasers, general relativity, and things like that. And so Queen's really gives you the opportunity to see various fields of physics and figure out what you do like, what you don't like. Is astrophysics really for you? So I think, going first into your undergrad and being like, which undergrad should I pick? That's like something that really drew me to choosing Queen's.
That is a great segue into the next question, which is how did you decide what university to go to? So we know why Anika chose Queen's. Maybe did someone else want to say a little bit about why they chose their university? Yes, go ahead, Martine.
Sure, I can address that. So as I mentioned before, I did my university undergrad degree in Virginia, and I am originally from Rhode Island, so it was a bit of a ways away. And the way I chose University of Virginia was mostly for its astronomy program, because I was already pretty sure I wanted to go into astrophysics in high school. So that was, a fairly big part of it, because a lot of programs, a lot of universities don't necessarily have an astronomy specialization or focus with their physics programs. Sometimes you would just do a straight physics program, which is totally fine as well. If you want to continue into astrophysics later, you don't need to do astronomy in your undergrad. But if you find that to be really interesting, make sure that I got some astronomy experience and that was a part of my courses, because I was worried that if it was only physics that I might lose interest or lose sight of sort of my ultimate goal. So that was important, but the other kind of aspects that are important are things like student life, the location, what kind of a city is it in. That stuff all matters a lot, because, a lot of your life in undergrad is coursework and homework, but you still have a life outside of that. And it's important to pick a place that you're going to be happy for the 4 years or 5 years that you're there. And so I would say you want to look at things like what kind of student kind of activities, clubs, organizations are there? And is it close or far away from your family? Are you willing to be that far away? Or would you like to stay closer? What kind of rents are there in the place you're going to need to live? Because finances can be an issue. Is it better to live at home? So those things all really factor in as well.
Mm-hmm. Did anyone else have any thoughts on the subject? Yes, go ahead, Catherine.
So another thing that, building on top of all these other choices that you need to make, I was also not 100% sure if physics was what I wanted to do. I was interested in chemistry as well. And so coming to Queen's, they have a general first year in the arts and science faculty. So I was able to take a variety of courses. And it also meant I didn't need to pick a major until the end of my first year, like after first year had ended. So I had the opportunity to change my mind if I needed to. And there was lots of room to be able to change my major if my projected major wasn't what I wanted to do. And so that made me feel a lot more comfortable in the decision I made, because I knew I wasn't locked into a set major.
Mm-hmm. All right, moving forward now, what kind of challenges do you face while conducting your research? Because it's not always sunshine and rainbows. Sometimes there are challenges that we can talk about. Does anyone? Okay, let's go with Karen. Oh, Martine, you had your hand up. Go ahead.
Doesn't matter, but yeah, research can be very challenging at times. And I think one of the challenges that I've been facing recently is that I've been working on a similar project for a couple of years now. And I really would like to wrap it up and move on to the next project. But sometimes there are certain factors that make a certain project go on for longer than you expected. And that's actually really common. You might go into a research project expecting it to be short and sweet and fully wrapped up within a couple of months or within a year. And Sometimes you find something new or exciting and you want to keep working on that. Sometimes advisors might suggest, more things to add on. Sometimes you might struggle and not get the results you wanted in a short time frame, and you might have to take a different approach. So it can be challenging when your plans don't end up going exactly the way you thought they would. But I think to be a good researcher, you have to be willing to make those adjustments and be flexible and be okay with, pursuing something for longer than you expected, or to know when to cut something off and consider switching projects if one isn't working out. And that can be disappointing and it can be frustrating, but it's part of research, and I think it's something every researcher experiences.
Were there any other thoughts on the challenges of research? Karen, go ahead.
Yeah, definitely. I mean, I think I have like similar experiences in that sense to Martine. I was doing my research at Copenhagen, which I love, about astrophysical neutrinos. But then, I started my master's, and I kind of changed that, not from neutrinos to dark matter. It's connected to what I do right now, but it's not exactly the same. So it was just a lot of knowledge that I have to kind of understand both. So, I have to kind of give one for another, but I still keep the collaborations now. And that's an important thing to, network along the way and keep those relationships growing. But yeah, definitely there's a lot of base knowledge that you have to have, but that's fine. You learn a bit more along with your research. You don't have to first know everything and then get to research.
All right, so a very, very pragmatic question next. Job prospects after getting a degree in physics. Are job opportunities available right out of the gate after finishing your undergrad degree? I know some of you are still in the midst of your undergrad degree, but it's something that is on a lot of people's minds, and we often talk about those kinds of prospects when we're trying to recruit people for undergrad. Maybe you have friends who finished a physics bachelor's degree and you saw them go off somewhere else while you were doing research. Go ahead, Martine.
So I can speak to that in terms of having friends who have gone on to, real jobs instead of into continuing their studies. So yeah, I had one friend who did an astrophysics degree and then went on to work for a private company that's working on a mission to Mars. So that was really, really neat, and she enjoys that a lot, and she gets to use her programming skills and the physics, knowledge that she learned in undergrad. I had another friend who did physics and environmental science, and she's going on to sort of environmental policy. So I think there's quite a few jobs in policy, in communications, in industry, and data science that don't require a graduate degree. So, and there's also, you don't have to go into something physics related either. There's definitely opportunities for astrophysics majors in things like consulting and finance. So there's a lot of opportunities, and I think it's a really good degree to have for job prospects.
Yeah, in the statistics that I've seen, people that have a bachelor's degree in physics are some of the most employable, and the starting salary that they get at the end of their degree is some of the highest ones. Maybe a little bit lower than people in computer science, because tech is tech, but otherwise it tends to be higher than biology or chemistry. So very, very good prospects for people who have a physics degree, even if it's just a bachelor's. But a bachelor's is hard enough, you earned your bachelor, you deserve a good job and everything after that. Were there any other thoughts on job prospects or stories that you have to share about what you've heard or people that you know? All right. If not, this is especially targeted to the people who are working with SNOLAB, who have worked with SNOLAB. What is it like to work in a big collaboration like SNOLAB? Anika, maybe? Did you want to?
I don't think I haven't done a research job at Queen's. I work a lot in student government in the summer times, but maybe Ashley might be better suited because I know she's done quite a bit of work with SNOLAB.
Sure.
So this summer I was able to join the News G collaboration, which is an experiment with like a sphere, and it's in Snow Lab, like way underground, that they fill with gas. And the end goal is to detect dark matter. So it was nice because there wasn't like too many people in at least the Queens section of NewsG. It's a collaboration with a couple different countries. So every week we would just meet with just the Queens one, and that was about 20 people. And those meetings weren't too long, and everyone was super nice. I mean, well, everyone in the collaboration was nice. And then there was one, I think it was once a month, there would be like a bigger one where we would meet with everyone. And since I was an undergrad, I didn't really talk at those. But I did talk a lot at the ones, or I did talk at the ones with just the Canadian collaboration people. But it was really cool to see kind of this huge collaboration and contribute to it a bit as an undergrad, because it's being done in a couple of different places. So yeah, that was definitely really cool for me.
Were there any other thoughts on big international collaborations? It doesn't have to be just Snow Lab. I mean, everybody, we all work in like these giant teams for the most part now, with like never-ending author lists on our papers. All right, if not, we'll move on to the next question. What are some tips and advice for students who want to obtain research internship opportunities at international research centers, or it could be normal research centers? So I'm thinking of you, Catherine, who had an NSERC USRA. Can you talk a little bit about that process, how that went?
Yeah, for sure. So last year, I kind of submitted an application on a whim. I had been submitting a lot of applications to our school's summer work program, and I decided to submit an application to NSERC on a whim. So that application was actually fairly short. You submit your transcript and you fill in some information about yourself, some of your award history. And through the program I applied to, it was the department at my school that picked the people who received the awards. And so on that application, there wasn't a lot that I could put forwards and explain about myself. So for some of the positions, grades are important, but there are definitely other positions that I applied to the summer work program that didn't need to see my transcript at all. So there's lots of different ways you can get positions.
Mm-hmm. And one thing I can mention is that for an NSERC USRA, you don't have to take it at your home institution. If you get that award and you have an agreement with a supervisor that's at a university on the other side of the country, and you just want to like you're in Montreal and you want to spend the summer in Vancouver working with someone at UBC, you can do that thanks to an NSERC USRA. So that's really a lot of fun. Karen, you've been around like internationally. You went to Copenhagen. Did you want to talk a little bit about how you found that research opportunity?
Right. So that one was very specific because it's a prize that is called the John M. Bacall Prize, and it's specific for Mexican students who are doing a physics undergrad. So that's how I got that one. But something that I do want to mention is that I remember clearly when I was in high school and I was very interested in astronomy. One thing, I had to do like a research internship when I was in high school for what I wanted to study at university. So what I did was just kind of like email a bunch of astronomers at the local institute. Just kind of like look for opportunities in your local community. So I think it's always, usually scientists are very responsive and want to help build a community. So don't be afraid to send a couple of emails and see if there are research opportunities around.
And once things are back to normal, even better than an email is a knock on someone's door, right. Because then they have to answer you right away, because sometimes things get lost in the inbox a little bit. So, but supervisors are always keen to talk about their research. Go ahead, Ashley.
I think also something important to help lead to a summer internship is to volunteer in things related to the job you want. So for example, Anika and I did a physics summer camp. So then when that's on your resume, profs kind of know that you're actually interested in it because you took time and, you didn't have to go and volunteer for that. But I think they like that a lot more, to see that you're involved in the community and passionate about being a part of it, as opposed to just having good marks. And I think that will help you like stand out, because I don't think all students do that in physics. So I definitely think that's something that helps set people apart. And I think that's part of why I got my research internship. So I would definitely recommend doing that.
Yeah, I definitely agree. I'm on a lot of selection committees for summer internships where I work, and grades are important, but they're not the most important thing. We ask for a motivation letter from our students and their CVs, and people that get involved in not just research, but also outreach, things like that. We really appreciate that in an application. All right, computer science. We are all very, very around our computers these days, but astronomers use a lot of programming specifically. Would a computer science degree be helpful for astrophysics research? Is it possible to do astrophysics grad school with a computer science degree? So I don't know if we've all have experience in computer science, but maybe you have friends who sort of made the jump. Yeah, Martine, go ahead.
Yeah, so I actually have a friend who did a computer science degree and is now in astrophysics grad school. So she did her degree in India, and so she's an international student here at U of T. And she did a computer science degree, but a couple of summers in her undergrad, she did a couple of astronomy related internships, and that helped a lot for being able to get into our PhD program. So I think a computer science degree, it's definitely possible to transition into astrophysics. It's not, the best way if you want to go into astrophysics. A physics degree is definitely the best way, but it is possible. And another thing that you can do is do a physics degree in computer science if ultimately you want to go into astrophysics, but you are also interested and you may want to pursue computer science or you're not sure. And so often in university, you can do a minor or you can do a double major. That can be a bit difficult with these kind of fields we're talking about because the coursework is fairly intensive. But I know people in undergrad who were doing those kind of double majors with computer science or math or other sort of STEM related fields, and they managed it. And it's a real advantage. I mean, if you have a ton of programming experience when you're applying to grad schools and you also have a physics degree, you're going to be a very attractive applicant to PhD programs because so much of our day-to-day is programming.
The next question is still a little bit computer related, but a very different spin. Given the pandemic, a lot of the attendees here will be starting university online. So do you have any advice for handling such a big change to going virtual with a university? Go ahead, Anika.
So I think one of the biggest challenges about going online, and I'm sure a lot of the panelists relate to this, is finding a study space that works for you. Often a lot of us associate our student homes with spending time with our housemates or a place for us to take a break and relax, whereas now they've kind of become our study bubble. And so I would say, as silly as it kind of sounds, make your study space pretty and comfortable, like light a candle, have your agenda out, things like that really help kind of make that space motivational for you. Something else that I kind of employed this past semester, actually, I didn't do this last semester, but you live and you learn, is something called the Pomodoro method. And you spend 25 minutes kind of working, no distractions, kind of put that phone away, and then you take a 5-minute break. And then after you do 4 of those chunks, you take a half-hour break. And then you do like maybe another 4 and you kind of take like a 2 to 3 hour break. And I find that that's kept me kind of going more efficiently on problem sets and things like that than just like sitting at my computer for 2 to 3 hours straight. I get a headache, I get restless. So I think that that's really helped. Just like getting up for 5 minutes, taking a loop around the house, and then coming back and sitting down. So don't forget to eat and fuel your body and move your body, and do things that make you feel good, especially when you're stuck sitting and staring at a screen all day.
Oh, really fantastic advice. Yeah, go ahead, Catherine.
Building on top of that, I agree with everything that Anika said there. And I also think another challenge is meeting new people when everything's online. And so something that I've started to do is try to friend the people in my classes on Facebook or other social media. And when I have questions on problem sets or some of the work, sometimes I reach out to them and try and build new connections that way and make new friends, because it's definitely difficult to meet new people outside of your established group. So that's something I would recommend as well. Don't be afraid to reach out to the people in your program.
Yeah, good advice. It could get a little bit lonely in this pandemic. And like we mentioned before, physics is so much about the community that you build with the people that are in the program with you. Okay, we're gonna just do maybe one or two more questions. Do you have any advice for students who are deciding between a physics and an engineering physics major? And I actually hear this question a lot because they're close, but not the same. Yes, go ahead, Anika.
This is a great question because I was actually in that position. I was trying to decide between engineering and physics and which one was really for me. I had a lot of family who actually did engineering at Queen's. So of course there was that factor of kind of your family pressures and things like that. I would say that maybe if it depends how much education, that might be something you weigh. So a lot of undergraduate students who complete an engineering degree don't go on to do grad school or maybe a master's and PhD. It's not as popular because they are offered kind of a huge wide range of careers straight out of like an engineering degree is kind of the most feedback I've heard about in terms of the amount of education. Whereas if you did your undergrad in physics, it requires a lot more theoretical learning and majority of students kind of move on to do a master's or a PhD. I would say the way I chose was really the courses available to me. I knew that I wanted to explore physics topics and learn more about things, whereas the engineering physics programs depend a lot about hands-on learning. They have a lot more labs than we do, a lot more lengthier and more in-depth labs about design and applications of physics and things like that. So I'd say those are kind of the major pinpoints. But another thing that Queen's kind of has is physics and engineering. Physics actually take a lot of courses together. I think like all 4 of my courses are EngPhys/physics based this semester. I'm sure Ashley and Catherine can relate. So you actually see a lot of the same content and probably have similar job prospects out of your undergrad. But that's kind of what I can say about that.
No, that's really fantastic that you had that experience of having to like make the decision between the two. So we'll go with one last question because it's a question that I always hear all the time. And then I'll give you each maybe like 30 seconds to like wrap up your thoughts, like one piece of advice that you would give to the attendees. So this one's the kicker. Do you need high 90s grades in high school to get into a physics program at university? Everyone is always worried about the grades. Go ahead, Karen.
Right. So you don't have to be like a straight A student. I mean, there can be a lot of factors for which you didn't get like A's in your high school, and sometimes it doesn't have to do with you, but the way that, you know, the courses are taught or other factors. I think that if you have motivation and drive, and if you really want to study a degree in physics, there will definitely be a university that will see that and, you know, admit you into the program. I think the most important thing is that you're passionate about what you do and you have a clear goal about it.
Mm-hmm. Were there any other thoughts? Go ahead, Ashley.
So I can't speak for other universities, but at Queen's, I know when you apply, you also submit a PSE, which is a personal statement about yourself and kind of like what you've done and your involvement in the community or sports. So I think Queen's, from my understanding, weighs that pretty evenly with grades. So although maybe you don't have the highest grades, you could have a really good extracurricular, and that kind of makes up for maybe not the best grades, and same with like vice versa. So I'm not entirely sure how it works, but I would say that grades definitely aren't the only thing that's important.
Maybe if anyone had a final thought on that, on the grades subject. Otherwise, what I can mention is typically physics programs don't have like a hard cutoff, or if they do, the cutoff is relatively low. Rather than think about your global grade, think about what your grades are in math and physics and how much you're enjoying math and physics. And just because your grades are a little bit lower, it doesn't mean that you're bad at it. It could be you're not clicking with the teacher, something else is going on in your life, lots of different things. So typically you can go into physics and then afterwards you can sort of suss out if you're enjoying it or not. And if it's just not for you, then you can sort of swap out. You can switch out to another program. So, all right, we're going to go ahead, give a little wrap up. Martine, final word of the day.
Sure, yeah, so university is a really fun and exciting and dynamic experience. If you go to university, you're gonna experience a lot of personal change and growth. I don't think anyone is the same person when they're coming out as they were going in. You change a lot, and that can be challenging. And so I think it's important to know that when you're starting university, especially if you're going into a physics program, it's a challenge. And you might feel like you're alone in struggling if you do struggle. But it's important to know that you're not alone. There's a lot of other students who are struggling with you, and you might just not be aware of that until you start to talk to your peers and start to form that community. And that community is what will really get you through a physics degree and help you to enjoy it. And it can be really, really fun. But I think there's not many people who do it alone. So I recommend, finding that community about the same things you're passionate about. And like Karen was saying earlier, just be open-minded and open to new topics of study, new research opportunities, and even potentially switching programs.
Mm-hmm. Final words from you, Karen?
Right. Yeah, I agree with everything that Martin said. I think the most important thing that I got out of university was a group of friends that I will keep for the rest of my life. So finding a community that understands you and that you can do homework problems together, because sometimes they're hard and you need to discuss the physics. I think that actually discussing the physics is what gets you to understand it in a deeper level. So definitely that. I think university is a wonderful experience, and I encourage everyone to go and experience that.
Awesome. Anika, final words?
Yes, for sure. So I echo what Martine and Karen have said so far. And I'll touch on just saying that university is truly what you make it. I wasn't even sure that I wanted to go to university, and it's truly been like the best 4 years, as they say. I would say, like, if I had to give one piece of advice, it would truly be get to know your school, get involved outside of your academics. You'll meet so many people from different walks of life that have different experiences to share. And I'd say what really made my university degree my own was what I got involved in my undergrad, whether it be clubs, physics student council, whatever your interests are, don't forget to explore them. These 4 years are for you, and don't forget to do that. So that's my little advice.
Awesome. And Ashley, your final words?
Yeah, so adding on to what everyone else has said, I think regardless of what program or what school you end up at, you will find like-minded people that I'm sure will be friends with you throughout your life, and you will find courses that you enjoy that will help you pick a program to stay in and love. And just kind of echoing what everyone else said, it is what you make it, and just try and get involved in everything you can and meet as many people as you can.
And finally, Catherine, your final words.
I would just re-echo the part about the community. I had a TA in first year tell me that you can't do physics alone. And I definitely say that's something that reaches from the undergrad level to all the research and the talks that we heard today. Physics is one big group project. So definitely reach out to the people in your physics community. And yeah, your undergrad's what you make it.
Awesome. Well, thank you so much to all our panelists and all our speakers from earlier today. Just to round up the day, we would like to thank again our incredible sponsors for helping make for helping Let's Talk Astrophysics happen and making it a success. So thank you to SNOLAB, the McDonald Institute, Queen's University, and a special shout out goes to Binder for the computational resources, and all of our volunteers, all the people behind the scenes and answering your questions, everything, making all this go very smoothly. Fantastic work. So that'll be it for today, and we will see you tomorrow at 1 p.m. Eastern. Thank you again. Have a good day, everyone.